A very good morning to all of you. We will continue with our discussion on magnetostatics. Towards the end of last lecture, we started looking at different magnetic materials, and let me recall. Magnetic materials. There are three primary types of materials. One are called diamagnetic materials, the other one is called paramagnetic materials, and the third one is called ferromagnetic materials. So, there are three primary types of magnetic response of materials: diamagnetic, paramagnetic and ferromagnetic. So, we started looking at diamagnetic properties. Diamagnetic. Let us recall that materials are made up of atoms, and atoms consist of the central nucleus, positively charged nucleus, in which the electrons are surrounding the nucleus and the electrons are orbiting around the nucleus. So, the electrons have an orbital magnetic moment associated with the orbital motion, and also are characterized by a spin magnetic moment. Spin is an intrinsic property of electrons, and it is just like charge and mass, etc. And you can picturize, but this is not a very correct picture, that the electron is spinning. It is called spin, and it has an associated magnetic moment with the spin. So, the total sum of the orbital magnetic moments and the spin magnetic moments of all the electrons of the atom gives me the total magnetic moment of the atom. So, I add up vectorially the magnetic moments of the electrons, including the orbital magnetic moments and the spin magnetic moments, and get a total magnetic moment of the atom. Now, diamagnetic materials are those for which the net magnetic moment of an atom is 0, no intrinsic magnetic moment. That means, the atom does not have any intrinsic magnetic moment. So, when exposed to an external magnetic field, dipoles get induced. By the external magnetic field. Now, according to Lenz's law, which we will discuss later, the induced magnetic moments are directed opposite to the applied magnetic field, the external magnetic field. And hence they produce a magnetic field. These dipoles will produce a magnetic field which opposes the direction of the external magnetic field, and such media will be repelled, will be pushed from regions of high magnetic field to smaller magnetic field. In an homogeneous field. So, unlike other materials which we are commonly aware of, these materials get pushed from regions of higher magnetic field to lower magnetic fields, and that is characteristic of diamagnetic materials. So, if you bring a diamagnetic material and apply an external field, the material instead of getting attracted is repelled by the magnetic field. Of course, the force of repulsion is very small, because as we have seen before, the magnetic susceptibility is very, very small, and this property is independent of temperature. It is also present in all materials. Of course, it gets masked in the presence of stronger effects such as paramagnetic effects and ferromagnetic effects, but it is present in all materials. And also the magnetization disappears when the external field is removed. So, in the absence of an external magnetic field, the medium has no magnetization and hence does not produce any external magnetic fields. When you put such a medium in an external magnetic field, the magnetic field magnetizes the medium, but the direction of magnetization of this medium is opposite to the direction of the external magnetic field. And because of this, such a medium gets repelled by the magnetic field and goes from a higher magnetic field region to a lower magnetic field region. And the moment you remove the external magnetic field, the magnetization disappears. So, we could write this equation m is equal to chi m h and b is equal to mu h, which is equal to mu naught into 1 plus chi m h for this media, and chi m, as we have seen, is much less than 1 and mod chi m is much less than 1 and chi m is actually less than 0. So, susceptibility is negative, but much less than 1, and hence the permeability mu is approximately equal to mu 0 for such materials, and they are an example of linear media in which B is proportional to H or the magnetization is proportional to the H vector. So, that is one class of media, and I have in the last lecture given you a table of typical materials which are diamagnetic in character. Now, let us come to the second class of media which are called paramagnetic. In paramagnetic materials, the individual atoms have a finite non-zero magnetic moment. So, atoms have a permanent magnetic moment. Unlike diamagnetic materials, individual atoms have a permanent dipole moment, magnetic dipole moment. Atoms with odd number of electrons have a net magnetic moment. Now, in bulk materials, in bulk matter, the dipoles, the individual dipoles are aligned randomly. Or aligned randomly, and hence magnetization is 0. That means, although individual atoms have dipole moments, in bulk matter they are all aligned in all directions randomly. So, if you add the individual magnetic moments of all atoms in a small volume, suppose I take a small volume containing thousands of atoms and I add up the magnetic moments vectorially of each of these atoms within this small volume, I will find it to be approximately 0. So, I will say the material is not magnetized because the average magnetization in the medium is 0. Although each individual atom has a magnetic moment, they are all aligned randomly at normal temperatures, and this random alignment means that magnetization is 0. On applying an external magnetic field, there is a torque on the magnetic moments which leads to partial alignment of the moments. Remember, we have seen earlier that if you have a magnetic dipole in a magnetic field, then there is a torque which acts on the magnetic dipole because of the magnetic field. The torque tries to align the magnetic moments with the magnetic field. So, although the matter does not possess any magnetic moment, the moment you put it in an external magnetic field, that external magnetic field applies a torque on each of the individual magnetic moments, trying to align them towards the direction of the magnetic field. Of course, this effect is counterbalanced partly by the thermal energy of the atoms, the thermal energy which is present because of finite temperature, and so there is not a complete alignment, but there is a partial alignment. And when there is a partial alignment, then the material gets magnetized. So, in the presence of an external magnetic field, the material gets magnetized, and the direction of magnetization is along the direction of the external field. So, the magnetic moment, magnetization generated in the medium is along the direction of the external magnetic field, and this leads to an attraction. So, the medium gets attracted towards stronger fields. In an inhomogeneous field. So, just like the common iron which gets attracted towards a magnet, this material, unlike a diamagnetic material which gets repelled, a paramagnetic material gets attracted towards higher stronger fields, and so it is exactly something like a ferromagnetic material, but it gets different from a diamagnetic materials. Now, in this case, magnetization depends on temperature. Because the external magnetic field is trying to align the dipoles towards the magnetic field, the temperature thermal motion of the dipoles is trying to misalign them or randomize them. So, in this case, unlike a diamagnetic material, magnetization depends on temperature, and so decreases with increasing temperature. temperature. So, in fact, Pierre Curie derived a formula (1859 to 1906), derived a formula for magnetic susceptibility, which is equal to C times mu 0 by T, and C is called the Curie constant. So, magnetization, the susceptibility is inversely proportional to temperature, and hence the magnetization will be inversely proportional to temperature, and such materials are, these are called paramagnetic materials. And just like diamagnetic materials, we can write M is equal to chi m h. In this case, chi m mod is again much less than 1 and chi m is greater than 0. We have again seen examples of paramagnetic materials in which I have shown that the magnitude of magnetic susceptibility is close to 10 to the minus 4, 10 to the minus 5, but it is positive. So, we can again write a relation P is equal to mu h is equal to mu naught into 1 plus chi m into h. So, in this case mu is greater than mu naught, it is very close to mu naught, but slightly greater than mu naught. In diamagnetic materials, mu is very close to mu naught, but slightly less than mu naught. So, this is the these are the paramagnetic materials, and these are formed by atoms which have a net magnetic moment in the absence of an external field. They have a permanent magnetic moment, but in the absence of an external magnetic field, they are randomly oriented, and so the material does not possess any magnetization. But in the presence of a magnetic field, they get aligned, partially aligned by the external magnetic field, which applies a torque on these dipoles, and this alignment leads to a partial magnetization of the medium, and we have magnetization proportional to the magnetic field, the H vector, and we have B is equal to mu H. So, again such media are linear media and can be represented by an equation B is equal to mu H. Now, we come to another very important class of materials, ferromagnetic materials. Now, in this case also, just like paramagnetic, atoms have an intrinsic magnetic dipole moment primarily due to electron spin. The spin of the atoms is the primary aspect which is responsible for the magnetic dipole moment. Now, in such materials, the interaction between adjacent dipoles is very strong, and this interaction has a name which is called exchange interaction. Which has an explanation through quantum mechanics. So, this interaction leads to a situation where minimum energy when neighboring moments are parallel to each other. So, this exchange interaction implies that the magnetic dipole moments of individual dipole moments all get aligned parallel to each other, and so there is a strong tendency for this to align, this exchange interaction to align adjacent magnetic moments in the same direction. But what happens is essentially when the material tries to minimize the total energy, the material gets subdivided into large number of regions called magnetic domains. Material subdivided into regions called domains. Each spontaneously magnetized to a high degree. So, the material gets subdivided into a large number of domains. Each domain is actually has a very strong alignment of the neighboring magnetic moments, and so it is highly magnetized. So, if you take a material like this, actually you can divide this into a large number of layers, larger number of regions, each has its own, this may be magnetized like this, this is magnetized like this, this is like this, this is like this, this is like this. So, these are all individual domains. Within a domain there are a large number of, so each domain volume is about is typically 10 to the minus 8 to 10 to the minus 12 meter cube. That is the volume of the each domain approximately. So, what happens is when you have a piece like this, the piece has a large number of domains, magnetic domains. Within each magnetic domain there are a large number of atoms whose magnetic moments are all aligned with respect to each other. So, this is a very strongly magnetized medium here, there is a very strongly magnetized medium here, there is a very strongly magnetized medium here, and so on. So, the domains actually adjust themselves to minimize the total energy of the system, and in that process what you find is a material like this which shows no external magnetic effects, because the magnetization, if you add them up, they all almost cancel to 0. So, there is no magnetization of this medium. So, when somebody fabricates such a medium and takes it out of a furnace, for example iron taken out of a furnace will have multiple domains in different directions, which minimizes the total magnetic energy of the system, and there are large number of dipoles. Each dipole has its magnetic moment oriented along some direction. So, the domain size, the number of domains, the shape of domains, etc., is determined by the minimization process, and this number of domains formation, etc., will take place until the energy gets minimized. So, if you have a big piece of ferromagnetic material, you will have many domains, large pieces of ferromagnetic media have many domains. Smaller pieces can be single domain. So, essentially it is a play between magnetic field energy and energy which is there at the interface between two different types of domains, two different orientation domains, and all the total energy gets minimized, and in that process the domains get aligned in random directions, giving you no net magnetization. So, this is a typical ferromagnetic material, but what is very important from this class of ferromagnetic material is, okay, it so happens that there are only 5 elements which show only ferromagnetic elements only ferromagnetic elements are iron, cobalt, nickel, gadolinium, and dysprosium. These are the only 5 elements which exhibit ferromagnetic behavior, and this explanation of this behavior requires quantum mechanics. So, we will not discuss this here in this course, but explanation of the ferromagnetic behavior of these materials requires quantum mechanics, and these materials are ferromagnetic, and there is a temperature called Curie temperature, which is such that for T greater than Tc, Curie temperature Tc, the material becomes paramagnetic. And so, if you have a piece of iron which is magnetized, which shows magnetic effects, if you raise the temperature of that piece to more than Tc, which is the Curie temperature of that material, then it loses its ferromagnetism and becomes paramagnetic. So, for iron, for example, Tc is about 1043 Kelvin. For cobalt, Tc is about 1400 degree Kelvin. So, different elements have different Curie temperatures. So, this is a very important temperature in ferromagnetic materials, that if you at any time raise the temperature of this material to more than Tc and bring it back down to less than Tc, the material becomes paramagnetic above Tc and becomes different as you lower the temperature. So, these materials have a very important and very interesting characteristic of magnetization. So, this is called hysteresis loop. Hysteresis. Now, to explain this, let me take the following problem. So, I take a toroid, we have discussed a toroid before, toroid of radius r of ferromagnetic material, and I wind it with a coil like a solenoid, closely bound wires around the entire circumference. Current goes in from here, current comes out from here. So, current is flowing through all these wires. Okay. So, I start with a piece of iron which is say fresh from the furnace. I have a toroid of this iron piece, and then I put a coil around this iron piece and pass a current. Now, what I want to plot is the dependence of H and B. So, suppose I will come back to this H, how do I determine H? So, what I do is I pass a current through this coil. As I pass a current, the current sets up a magnetic field, and that magnetic field magnetizes the piece of ferromagnetic material. And we know that the ferromagnetic material, when a material is magnetized, it produces its own magnetic field, because a uniformly magnetized piece is equivalent to a surface current, and that surface bound current creates its own magnetic field. So, suppose I were to plot the dependence of magnetic field on H. Remember, for paramagnetic and diamagnetic materials, B is linearly related to H, they are called linear media. So, now what happens is I start from this point where there is no magnetic field of this inside this material, nor is there any H field. Now, I start passing a current. Now, remember, we have an Ampere's law. So, let me assume that the thickness of this toroid is very small compared to the radius. So, what is Ampere's law? Integral H dot dl is equal to I free enclosed. H is the H field, and I f enclosed is the free current enclosed, that is the current which is actually conduction current passing through the wire. So, if I take a loop like this, remember we have done this problem before in an earlier lecture. I take a radius approximately capital R. and because of symmetry H will be the same at all points, and as we have seen before H is in this direction, in the direction of this circle here. So, I can immediately integrate this and I get H into 2 pi r is equal to, if the number of turns, total number of turns is n t and the current passing is I, the total current enclosed by this loop, Amperian loop, is there are n turns, each turn carrying current I. So, the H field is actually n t by 2 pi r into I. So, as I change my current, I change the H field inside, and as I change my H field, I change the B field and I plot B versus H. So, I start from here, when there is no current initially, there was no H, there is no B, and I start to increase my current. As I start to increase my current, H starts to increase in the positive direction, and I find that the magnetic B also increases and gets saturated. So, let me call this A and it goes to some point B. So, as you increase H, B increases, but not linearly, non-linearly, and then if you increase H to a larger value, it tends to saturate. That means, there is very little increase in B as you increase H. That is a magnetization curve, and so if you see here B by H, which is called the mu value, is not independent of position, it is dependent on the H value. So, B by H ratio here is different from here, is different from here, because this is not a straight line. Okay, so, I go like this. Now, what I do is I reduce the current back from I to 0. So, what happens is this material does not retrace its path, but comes to a point here, and let me call this C. So, when I decrease my current, I do not come back to the same point Z, this point I do not retrace this curve, but I retrace another curve. So, at this point H is 0, which means there is no current passing through the wire, but the material shows magnetization, there is a magnetic field, and that magnetic field is because of the magnetization of the material. And as you can see here, when you remove the external magnetic field, when you remove the H field, the material still has a magnetization. So, it is a permanent magnetization. You can, even if you have a ferromagnetic material, apply a magnetic field and remove the magnetic field, initially it was not magnetized, but after applying a magnetic field and removing the magnetic field, the material becomes magnetized. So, there is a permanent magnetization, which remnant magnetization. So, what happens is at this point there is still a magnetization, there is still a B field, but no H field. And if you decrease the H to negative values, that means pass current in the reverse direction, the current, the curve follows like a path like this, and on the other side it gets saturated. So, let me call this D and this is E, and then if I start to decrease H, the curve follows this path, and then it comes like this and goes back. So, this is called a hysteresis loop. This implies that the B field and H field are not in phase, B field lags the H field, and this name hysteresis comes from a Greek word which means to lag behind, And so, as you can see here, this field as the H field increases, the B field increased, it got saturated, then as you start to decrease the H field, the B field decreases, but not in the same fashion as when it was increasing. It then becomes, it hits the vertical axis at this point H is 0, but there is a finite B field, and as you decrease the H field further to some value here D, it becomes B becomes 0, but H is finite, and then it saturates on the other side and comes back. So, this is called a hysteresis loop, and this is a very, very important property of ferromagnetic materials. So, there are two important points here, one is this point C and one is this point D. So, what is at point C? Look at point C, what it implies is even after you have removed the current from the coil, that means if you remove the coil, there is no current passing through, H is 0, but B is finite. So, this point C is referred to as remnants. So, as you can see here, when I reduce the H field from B, the magnetic field B decreases and we hit a point C at which H is 0, but B is finite. And then when you decrease the H field further, B becomes 0, at this point D, and the hysteresis loop gets completed like this. Now, there are two important points in this loop, one is this point C and one is this point D. So, let me write down what this point C is. The point C, that is called remnants. So, this is the point C, which is referred to as remnants. This is the value of B when H is reduced to 0. That is, as you can see here, when I reduce H from here, the loop does not follow the loop in this direction, it comes back and hits this point C. So, this point C has 0 H, but a finite B, and it is called remnants, and it is usually denoted by this quantity B r. This is the B r, which is the remnants, and this is a very important point. And as you can see here, even when I have stopped the current in the loop, there is still a magnetic field within the toroid here, and that is a characteristic of ferromagnetic materials. Paramagnetic materials, as soon as you reduce the current to 0, the magnetization disappears and the magnetic field disappears. Here there is a magnetic field still with the ferromagnetic material. Now, as you decrease H further in the negative direction, as you increase H in the negative direction, we will hit a point D, and this point is again a very important point here, which is called this value is called coercive field. So, this is the value of reverse field H required to drive B to 0. So, this is represented as H c, this is the field. So, remnants is this point C, where the field B is finite with H 0, and coercive field is the value of H required to make B as 0. So, these are two very important characteristics of ferromagnetic materials. So, if you have this is B. So, let me write mu naught H here, and mu naught H and B have the same dimensions. This is in Tesla, this is also in Tesla. So, some typical numbers here. So, this is 1.0, this is 0.5, this is 5, 10, 15, etc., and this is into 10 power 4. So, if you have 10 times 10 to the minus 4 Tesla of mu naught H, you generate about 1 Tesla of B field, and as I will show through an example, this implies very, very strong fields generated by the magnetized material. So, let me look at an example. So, this is the toroid radius. So, let me assume a radius of 5 centimeter and number of turns 100. So, as we have seen, H is equal to N T I by 2 pi r, and if you pass a current of say 0.3 amperes, H is equal to 100 times 0.3 by 2 pi into 5 10 to the minus 2, which is about 100 amperes per meter. So, that is about 100 amperes per meter, and suppose the coil. So, there is a coil here, let me draw the coil. Now, earlier remember when we were discussing toroid, we did not assume any presence of any medium here. So, let me if there was air, for air core, that means if there was no material here, but just air, the corresponding B will be mu naught H, which will be equal to 4 pi 10 to the minus 7 into 100, which is equal to 4 pi 10 to the minus 5 Tesla. So, if the core was made of air, which means there is no material there, then you would have got a B field which is about, this is about 112, so it is 1.2 10 to the minus 4. As you can see here, compared with this ferromagnetic material, it produces 1 Tesla. Now, let me calculate with iron core. With iron core, if I pass the same current of 0.3 amperes, H field is the same. So, H is still 100 amperes per meter. Now, see here, I must have an estimate of the mu. Now, one of the problems in this hysteresis is mu is not very well defined, because mu, as we have seen, is the ratio of B to H, because we had written B is equal to mu times H. The value of mu depends on where you are on this curve. So, that is why such materials are called nonlinear materials. There is this relationship B is equal to mu H has to be used very carefully, because mu is not well defined. For example, at this point B is finite and H is 0, which means B by H ratio is infinite. At this point B is 0, H is finite, so B by H is 0. So, mu goes from infinity to 0 here. So, you see mu can have any arbitrary value depending on where you are. So, in such materials, to have a value of mu, one has to be a little careful, but you can actually have a, you can put yourself at some point of operation and define a mu. So, if my relative permeability typically for this materials is about 10,000, I can have, then the B which I will produce, sorry, B is equal to mu H, which is equal to mu naught mu r into H, which is equal to 4 pi 10 to the minus 7 into 10 to the power 4 into 100, which is about 1.2 Tesla. So, the same current of 0.3 amperes, a current of 0.3 amperes was producing a magnetic field of 1.2 10 to the minus 4 Tesla with air core. The same current now with a ferromagnetic material produces a magnetic field of 1.2 Tesla. So, in the presence of ferromagnetic materials, because of the magnetization of the medium, that magnetization is extremely strong. That magnetization leads us to a very strong magnetic fields in the presence of ferromagnetic materials. Now, suppose I had an air core and I want to produce the same field. For producing same B with iron core with air core, remember H is equal to, for air core, B by mu 0, which is equal to 1.2 by 4 pi 10 to the minus 7, and that must be equal to NTI by 2 pi r. So, the current required I can calculate from this equation. I is equal to 2 pi r by NT into 1.2 by 4 pi 10 to the minus 7, and that comes out to be 3000 amperes. A very large current is required to essentially produce the same magnetic field with air core. So, use of ferromagnetic materials can help us to generate extremely strong magnetic fields even with very small currents. So, how is this happening? This is happening because the ferromagnetic materials get magnetized, and those magnetization are very strong, lead to a very strong atomic currents or magnetized bound currents in the medium, and those bound currents produce very strong magnetic fields and help us to achieve extremely strong magnetic fields even with very small currents. So, this is a very important aspect of ferromagnetic materials, and so ferromagnetic materials are used in many places wherever we need very strong magnetic fields, such as transformers or such as loudspeakers or electromagnets and so on. So, we need to have magnetic very strong magnetic fields in these cases. So, I must just differentiate between two types of ferromagnetic materials. So, you can have two types of hysteresis loops, primarily one where the hysteresis loop goes like this, H versus B, another one which So, the difference between these two is, as you can see here, the coercive field here is very large compared to the coercive field required for this. These are called hard ferromagnetic materials. These are called soft ferromagnetic materials. So, they have different kinds of applications. Wherever you want permanent magnets, I must choose hard ferromagnetic materials, because in such materials coercive field being large implies that the field required to demagnetize the material is extremely large, and so environmental effects are very minimal in these permanent magnets. They can retain their magnetization at room temperature over a long duration. The soft ferromagnetic materials are used in things like transformers or loudspeakers and so on, where you want the material to lose its magnetization as soon as you remove the external current, and these are soft ferromagnetic materials. So, both such magnetic materials exist. Okay. So, three primary types of materials: diamagnetic, paramagnetic and ferromagnetic materials, and these materials have very strong magnetic properties. Ferromagnetic materials have very strong magnetic properties. Diamagnetic have negative susceptibility, but very small. Paramagnetic have positive susceptibility, which is very small but positive, and ferromagnetic materials have nonlinear characteristic, and hysteresis loops are very important parts of such ferromagnetic materials. So, with that we finished our discussion on materials, and what I want to do now is to look at a very interesting aspect of magnetism, and that is Earth's magnetic field. Now, our Earth is associated with a magnetic field. That means surrounding us there is a magnetic field which is there as a part of the Earth's field, and this Earth's field is almost like a dipole, like a field produced by dipole. That means just like a solenoid or a current carrying loop, it produces a field, and this dipole field is generated by the Earth itself. Now, people have been investigating the origin of these magnetic fields, and it is believed that at the center of the Earth is a solid iron core consisting of primarily of iron at about 5700 degrees centigrade. And because of enormous pressures, the material is in a solid form. Surrounding this is a region of liquid iron and nickel, and that is molten in the molten form. It has iron, nickel and small quantities of other materials. Now, because of differences in temperatures and pressures, there is a flow, convection flow of these metal particles within the fluid itself within the fluidy core of the Earth. And this convection current leads to movement of ions, and these generate currents, and these currents essentially lead to the generation of magnetic field. So, this is the current theory called the dynamo effect, and the fluid which primarily consists of iron, nickel and small quantities of other materials is actually circulating, and in that circulation it produces currents, and those currents leads to magnetic fields, and the magnetic field is almost like that produced by dipole. Now, there is a very interesting aspect to the Earth's magnetic field, and that is the following. So, let me draw, for example, so let me draw the Earth here. This is the Earth. We all know that the Earth is spinning around an axis which is inclined to the vertical. So, the Earth is rotating in a plane around the Sun. It is rotating around the Sun in a plane, and the axis of rotation is not perpendicular to the plane, but inclined at about 23.5 degrees inclined. So, this is called the geographic north, and this is called the geographic south. So, the equator is like this. Now, it so happens that if you take a compass, we had seen a compass before, if you take a compass, it does not orient towards the geographic north, it orients at a slightly different position, and so we define what is called as a magnetic axis this is the magnetic north, and this is the magnetic south, and this angle is about 11.5 degrees. This angle is about, so Earth's axis of rotation is inclined to about 23.5 degrees with respect to the perpendicular or to the plane, and the magnetic axis is slightly displaced with respect to the geographic axis by about 11.5 degrees. So, if you take a magnetic needle, the north direction of the magnetic needle does not point exactly towards the geographic north, but slightly tilted. What is also found is that the north magnetic pole is called north magnetic, it is called north magnetic, but that means the north pole of the magnetic compass points toward the direction. So, that must correspond to the south pole of the dipole magnet. So, if I were to draw a dipole magnet here, this will be the south pole and this will be the north pole. So, if let me draw another figure here showing the field lines, what it will look like. So, I have the Earth, the geographic one, this is the, so north geographic, north magnetic, south geographic, south magnetic. So, the equivalent magnet looks something like this. This is south, this is north. If I were to draw field lines, you have something like this. It's approximately dipolar. So, the field is not exactly it's like a dipole, it's approximately dipolar. So, suppose you were to take a magnet, a compass needle at some point, what you see is it points in a slightly different direction. So, let me show you through a demonstration here. So, let me take a pair of pencils. So, this red pencil points towards the north, geographic north, and the black pencil is pointing towards the geographic east. This red pencil is pointing towards geographic north, and the black pencil is pointing towards geographic south east. So, if you take a magnetic needle here, if you take a magnetic needle, it will point like this. If the magnetic needle was free to rotate in any direction, it will point like this. It is not pointing towards the geographic north, nor is it in the horizontal plane, it is pointing like this. So, let me repeat, this is the geographic north direction here, this is the east direction here, and if I take a magnetic compass and allow it to be freely rotating in any plane, what I find is it does not lie in the horizontal plane, but it points slightly downward and in this direction. So, now I define two angles, the angle between this vector and the horizontal plane, which is this angle, is called the dip, and the angle between the horizontal line and the geographic north is called the declination. So, let me recall again here. So, if I this is the magnetic field direction, I go up to the horizontal plane, I get the dip, and I move this angle towards the geographic north, I get declination. So, there are two angles here. From the direction of the B vector, I move a certain angle which is called the dip to come to the horizontal plane. So, the angle between the magnetic vector and the horizontal plane is called dip. The angle between the horizontal component and the geographic north is called the declination. So, these two angles represent the direction of the magnetic field at any point. So, geographically at different points you will have the definition of a dip, which is this angle between the magnetic field direction and the horizontal plane, and a declination between the horizontal component of the magnetic compass and the geographic north. So, if you allow the magnetic needle only to rotate in the horizontal plane, it will point like this here and not like this, it will point like this, and this angle is actually the declination, and one has to correct this for in geographic conditions, because this direction of the magnetic compass is not exactly the geographic north, but it is the magnetic north. So, these two angles are important angles from the point of view of the Earth's magnetic field, the declination and dip. So, declination angle between geographic north and horizontal component of magnetic field and dip or inclination is the angle between horizontal plane and the field direction. So, these two angles are important angles from the perspective of Earth's magnetic field, and they are important parts of the Earth's field. So, for example, let me just give you some numbers here. In New Delhi, the declination is about 1 degree and 7 minutes, and inclination is about 44 degrees 37 minutes and towards east. So, we can get a table of declination and dip at different positions on the earth, and these two are very important parts of the Earth's magnetic field. So, as you can see here, we have essentially the Earth is approximately a dipolar field. The orientation of the magnetic field at any point on the surface of the earth is not horizontal, it is tilted. Also, the direction in which the north pole of the magnetic compass points is not exactly the geographic north pole. So, there is an angle, and so explorers have to correct the orientation of the magnetic compass needle to get the exact geographic north wherever they are on the earth's surface. And both these angles change as you change the position on the earth's surface. In fact, towards the north or south pole, the magnets will be pointing vertically, and so this is a very important aspect of Earth's magnetic field. So, let me finish the lecture by just summarizing very briefly what we have discussed till now. In magnetostatics, we started with Biot-Savart law, which gives me the magnetic field by a current carrying conductor. Then we discussed magnetic forces on moving charges, and as an example we looked at a particle accelerator called the cyclotron. Then we discussed the field produced by current carrying conductors, circular loop of coil and a straight conductor, and obtained the Ampere's law from there, which is a very, very important law. We then introduced the concept of magnetic dipole moment, looked at the torque on a magnetic dipole moment in an external field, potential energy of a magnetic dipole moment, and from there we discussed an example in terms of a moving coil galvanometer, voltmeter, ammeter. And then we looked at different magnetic properties, diamagnetic materials, paramagnetic materials, ferromagnetic materials, and finally a small simple discussion on the Earth's magnetic field. Thank you.